Uh, Welcome. Our speaker today is Xian Tang, and his title, as you can see there, is Morita Invariance of Groupoid Cohomology. Please, Xian, go ahead.
Thank you. Thank you to the organizers, Willie and Gisela, for the invitation. It's a great pleasure today speaking in our seminar and discuss mathematics with the participants. So my talk today is about my recent study of Morita invariance. Let me do the Morita invariance of groupoid cohomology. So let me do the groupoid cohomology is a natural generalization of group cohomology. Like, when we study group cohomology introduces us a lot of fundamental invariants for groupoids, and it has been widely used in the study of differential geometry, system algebra, and Lie theory, dynamical integrable system, many different areas of mathematics. So in the study of groupoids, there is a fundamental relation which is called Morita equivalence. The concept of Morita equivalence was introduced in algebra, in the study of calligraph modules first, and now it is now a fundamental equivalence relation in the study of groupoids. It is a generalization of orbital equivalence. So what we are trying to study in this joint work, in this talk, is about Morita invariance of the cohomology theories on groupoids. Okay, so that is a big abstract or the sketch of my talk. So now the plan of my talk today has three parts. In the first part, I will try to introduce briefly a groupoid and also Morita equivalence of groupoids. So for my talk today, I will focus on smooth version, so Lie groupoids. And in the next part, I will introduce the groupoid cohomology. Okay. So we will, again, since I'm just said, I will focus on the smooth version. The groupoid cohomology will also focus on the C infinity version. And then in the last part, I will explain the Morita invariance property for groupoid cohomology. So that's the plan of my talk. So before I start discussing mathematics, let me introduce you my collaborator. So this is my collaborator, Joel Villatoro. So he was a postdoc in the last 3 years, and now he's a lecturer at University of Indiana at Bloomington. Okay. So now let me start with, I should click that introduction to groupoids and the Morita equivalence. So groupoid is a generalization of groups. So it is a concept that unifies both the internal and external symmetries of an object. So as a generalization of group, it has more than one unit. But other than that, it carries essentially all the properties as group. So let me get into enter the definition. The groupoid from the category point of view is a small category with invertible morphisms. So it's a small category, which means that this collection of objects is a set, and also the collection of morphisms is also a set. So with that, we have two sets, right? We have a set of objects and also a set of morphisms. So let me write. So usually we denote a groupoid with the set of morphisms, and then we write two arrows and then the set of objects. The two arrows refer to the source and target maps. So basically associate to a morphism, we know where does the morphism start, the object it starts with, then the object it ends with. That's naturally give us two maps. You can see the source and target maps. In literature, there are also maybe S and R or maybe other notations for the source and targets. So for my talk today, we will choose a convention. The convention is I will think about the arrows goes from the right to left. So let me maybe draw it here. So this is our arrow G, and then we have the source of G and the target of G. Of course, if you like, you can swap the orientation, and then everything we're discussing has a version in the other order, in the other orientation. But for the convenience, we'll just keep this as our convention. Okay, and then let's continue. So the difference between the group and the groupoids is kind of lives in this one. So when we study multiplication, when we study the operation, for group, we know giving us any two elements, we can take the product. But for groupoids, we cannot do it. We can only do it when the arrows are composable. So here it means we have one arrow, G1, and then the other arrow, G2. Only when the source of G2 agree with the source of G1, we can take the product. So when this happens, we have a product. This way, there's G2, G1. Okay. So that's the multiplication, and then the left of the structures are kind of easy to understand. We have the identity morphism to inclusion of the set of objects associated to each object. We have identity morphism. That's the identity, embedding later. And then we also have the inverse. So that's the structure we have on a groupoid. So in my talk today, we will focus on the Lie groupoids. So we will look at the generalization or maybe the objects, groupoid objects in the category of smooth manifolds. So there's a little bit more assumption we need to require in order to work with the construction, in a better way. So let me introduce that. So a Lie groupoid, first of all, it's a groupoid. Both arrows and object sets, they are now smooth manifolds, and all the structures are smooth maps. The actual assumption we're making here in many times in the study of the Lie groupoids is we require the source and target map to be surjective submersive. So this is a little bit more than smooth manifold. So we need this in order to require, I'll mention it in a moment, in order to have this composable pairs, the set of composable pairs to become a manifold.
Sorry, surjectivity is automatic because U is right inverse of both S and T, right? So
right, the surjectivity is automatic. The real requirement is the submersion, the submersive. Is with that we can do fiberation of manifolds over the source and the target maps. Okay, so the other remark is, in general, we require this unit space to be a Hausdorff manifold. And for the space of arrows, there are many interesting examples from geometry. For example, from foliation theory, when we consider holonomic groupoid, the G1 is not a Hausdorff manifold. So this is an assumption sometimes we need to kind of weaken. So we don't allow G1 to be Hausdorff. Instead, the kind of the makeup is we will require the source fiber and the target fiber to be Hausdorff. They are smooth manifold in the usual sense. But throughout my talk today, I would, just to simplify our discussion, I will consider G1 to be Hausdorff. In this way, we don't need to talk about the right definition of smooth functions on a non-Hausdorff manifold. So that's this D theory. And now, just, a very widely used concept, a special class of groupoid is called étale groupoids. So when the source and target are local diffeomorphisms. So this goes beyond the smooth groupoid, even for topological groupoid, you can say étale when the source and target, they are local homeomorphisms. And the next is the proper groupoid. So the proper groupoids, they refer to groupoids that this map, kind of the product of source and target map together to the product of the unit space. When this one is proper, we call the groupoid proper. So this is a generalization of proper action for group action. Okay, so that's the quick introduction of Lie groupoid. So now let's look at some examples. I assume many of us are familiar with it. So let me go through them quickly. So as I mentioned, groupoid, includes the group action. So we can consider a Lie group acting on a smooth manifold. So it could be a discrete group, or maybe, with non-trivial manifold structure. Then we can consider the following groupoid structure. The space of units is the manifold itself. And then the space of arrows consists of the product, a pair of element in G and element point in M. And we have the following structure. And we use this, since it's a left action, we will use this notation for the groupoid. And this is usually called the transformation groupoid. Also, sometimes in literature, we call it action groupoid. So the source and target are defined. Remember, I mentioned to you in my talk today, our arrows goes from the right to left. So we'll think for a pair, okay, maybe. We think that we're mapping M to G times M. That's the convention. So now, the group action properties make our structure, the composition in this way. So basically, you can see the action property make our groupoid a multiplication structure, and it's associative, and we have the inverse. And now the groupoid, the transformation groupoid, is étale. So which means that both source and target maps are local diffeomorphism. That will require our group actually to be a discrete group. So in general, if the group is not discrete, then the groupoid is not étale groupoid. Of course, there are étale groupoids, not from group action. So the next is, the group, this I just mentioned, the groupoid is proper if and only if the group action is proper. So that's this class of examples from group action. The other one we will see in my talk today is the pair groupoid. So this is, start from a manifold. Now, what do we consider? We consider the space of units as the manifold itself. And then we have arrows, just a pair of points in the manifold. So this one shows up very naturally in the study of geometrical analysis on the manifold. So for example, when we consider operators, there's, we have smoothing operators, the kernel functions, they are really functions on the product of manifolds. And now, given us the pair of points in the manifold, we have the source map and the target map, taking the first component and second component. Yeah, I'm sorry that because I have chosen the orientation of arrows going from right to left, so my convention of the order of points is also swept. M2, M1 instead of M1, M2. Yeah, please bear me with that. And then the composition is basically, we forget the middle point, right? So we have the composition of arrows in the pair group. And then the inverse is to swap the 2 points. So this structure together is called the pair groupoid. Yeah. And now, when is the pair groupoid étale? It is étale, if and only if M itself is discrete. So if M has non-trivial dimension, then this is not the étale groupoid. And the other property is this groupoid actually is always proper. So the next I want to discuss about the Morita equivalence. Before that, any questions? Okay, so I don't see any.
We're fine.
Okay, great. Let's continue. So the next I want to discuss Morita equivalence. So before that, I want to talk about the morphisms of groupoids. So the idea of this is very simple. Basically, it's a functor of categories. But now, of course, when we have Lie groupoids, we want the functors to be compatible with the manifold structure. So we need a pair of smooth functions, right? So maybe I'll try to draw it. We have H1, H0, we have G1, G0, and then we have a map on the morphisms. We have maps on the objects, and it will require this to be compatible with the groupoid structure. That's what's written here, the target, source, and composition. Okay. So that's the morphisms of groupoids. So for Morita morphisms, or the weak equivalence, we will look at so here, a special type of morphisms. So we need to require something here, which we call smoothly essentially surjective. It's mainly the essentially surjective here. So what is this? You can see that we have a map from N to G0. So now what we hope is we hope the map N to be surjective down to the space of orbits of G0. So the map from N to G0, this map itself may not be a surjective map. But we want that, okay, when we look at this fiber product, now you can see why we need the S to be submersive. When S is a submersion, the fiber product always carry a smooth structure. So we can talk about the smooth function. And then we require that this map to be surjective submersion. So basically this says that for every orbit in G0, it has a non-trivial pre-image. Although the F map itself may not be surjective. That's the property we need to define the weak equivalence. So basically, at the set of orbit level, the map is surjective. Okay, great. So now, with that, we can talk about pullback of groupoids. So we have a map, a smooth, essentially surjective map. So for give us such a map, we can define a groupoid by pulling back G to N. We will use the upshrink as kind of, the an analog of what do we have in the sheaf theory. We have the upshrink map as a pullback. So as the space of units, it is the manifold M, but now for the space of arrows, we are doing this fiber product. So I guess we can draw it in a little bit like this. So we have G0, G. Now we have a map. This is N. So what we are trying to see as arrows here is now G has arrows like this. But now for M, we will have one point. Let's say this is the point in N, but it's mapped to the F of N2, right? And then we have an arrow here. That's the G arrow. And then we have N1. So this is the picture of arrows. And now with this, we can define the structure of groupoids following this kind of geometric, notation. So the source and target is basically the first and the last. And the multiplication is, we throw away the middle points and then take the composition of two arrows. So that's the pullback of groupoid. By the way, to the definition of pullback of groupoid, it's not necessary to consider smoothly essentially surjective maps. We can define it for more general maps. But for the Morita equivalence, I will need to consider such essentially surjective maps. So that's why I introduce it. So now let me tell you the Morita equivalence. So as I mentioned, the Morita equivalence, the concept goes back to T.T. Morita in the study of category of modules of rings. So it's a ring theoretical concept. In the 80s, this was introduced into groupoids. Now it is a fundamental concept in the study of system algebras and also geometry of groupoids. So now let me go to the concept called weak equivalence. So weak equivalence is a special type of groupoid homomorphism. You recall, for the groupoid homomorphism, we have a pair of maps on the units and also on the morphisms. But now what we require is, when we pull back the groupoid, this map, this F map, mapping H to this one actually is isomorphism of Lie groupoid. So basically we're saying that when we pull back the groupoid G through this F0 map, we get isomorphism. H and the pullback are isomorphic. So when we say isomorphic of Lie groupoids, we mean that also it's compatible with the smooth structure. So with this, we can define the Morita equivalence. So basically it says that if we have two groupoids, we can have maybe say G and H. So we may not be able to find a morphism directly from H to G. So we may have to consider some maybe U1. Okay. So we may have to have a U1. It is equivalent to G, and then maybe U2 equivalent to G1. Then we have U2 and then H. So we may have to do some zigzag form to get to the equivalence between G and H. So once we allow this, yeah, Willie, you have a question?
Yeah, I have a question. So, I mean, starting, so I was expecting that there will be correspondences, groupoid
Yes,
correspondences.
yes, it will be.
Yeah, but apparently you are building like a free correspondence out of the map from N, because the action, I mean, to have a correspondence, you need to have a G space. And to have a G space, you need to have an action. Now,
Yes.
you are building the action by taking this two-sided uh, two-sided pullback, right?
Yeah. I'm getting there in the
Okay,
next.
okay, but apparently you are restricting yourselves to very particular correspondences, like
Yes.
the
I
ones.
want to. Yeah.
Okay, okay.
Yeah. Yeah. You are right. You are right with the point of view. Yeah. So actually, one can, unify this kind of zigzag weak equivalence using the kind of intermediate groupoids, or in the bibundle picture, it's the following. That's what I want to remark. So we have on one side, we have H. The other one, we have G. And then we have some bibundle in between. So one is the sigma map, the other rho map. We require that P has a, left action of H and the right action of G. We require both actions are principal, meaning that they are free and proper. And the as sigma map, this one is a principal G bundle over G H0, and the rho is a principal H bundle over G0. And with that, we can do the following. So we can follow what I discussed here, pull back this groupoid to P. We can also pull back this groupoid to P. With the correspondence property, we can actually check the two pullbacks to P, they are isomorphic. So this is the probably more commonly used in some version of Morita equivalence using bibundles or the correspondence, as Willie mentioned. And the weak equivalence here has some nice properties because there's a natural morphism. So it's kind of a balance between working with either this version, the Morita equivalence, or the weak equivalence. So any other questions about this concept? I hope now this is clear. Okay, now let's continue. So let's look at some examples. The first example is about the groups. So for groups, we have only one unit. So we can check the two groups are Morita equivalent, if only if they are isomorphic. So at the group level, we are not defining anything new. The next one is about the pair groupoid. Here, pair groupoid is Morita equivalent to a point. So you can say that, well, for the pair groupoid, we have any 2 points in the unit space, they are equivalent. They are connected by an arrow. So when we look at the space of units, modulo the orbit equivalence, there's only 1 point, and we don't have any internal symmetry because there's no arrows starting and ending at 1 point. With that in mind, the two groupoids should be equivalent. So that's why it is heuristically equivalent to a point. So in general, the Morita equivalence carries kind of two pieces of information. One side, it tells us the orbits, set of space of orbits, they are equivalent. Also, at the level of isotropic groups, they are also isomorphic. So Morita equivalence contains, these two parts of information. Now the next one is this kind of a groupoid associated to submersion. So this is more like foliations, if you are familiar with foliation. So we have the fibration map from M to P. And then we can look at a pair of points over the same fiber, right? Over the same fiber. That's this fiber product over P. So we look at the points mapped to the points of M mapped to the same point in M. And this form a groupoid. This groupoid is actually Morita equivalent to M. So this is again this kind of along the same line as the orbit equivalence. So the other one is from the group action. So in general, if the group action is proper and free, then the groupoid, the transformation groupoid, is Morita equivalent to the space of orbits. So this actually goes beyond the group action, even for proper groupoid. If the action is proper, meaning that the groupoid is proper. If the groupoid is free, meaning that there's no non-trivial isotropy groups, then the groupoid is actually Morita equivalent to the space, the manifold of space of orbits. Okay, great. So that's about the Morita equivalence.
Can I ask a question?
Yes, please.
You say is a Morita equivalent to the space of orbits. What's the groupoid structure on M modulo G?
Very good question. I did not specify it. So when we have a manifold, here I have a manifold, here is a point. When we have manifolds or when we have a set, we view them as this kind of a trivial groupoid. So we just think, so let's say let's take this example, M mod G. So the space of orbits is, the unit space is M mod G. And we only have trivial morphisms. The space of arrows is also M mod G. So we have only identity morphisms.
Okay.
And on this groupoid, the composition, the multiplication of morphisms is trivial. So there's no non-trivial composition of arrows. So although we have source and target map, they are both identity maps.
Okay, yeah.
Also, I just wanted to remark that these conditions are not just necessary for the Morita equivalence to hold, but for M/G to exist in your category, because you want this to be a smooth manifold, right?
Yes, yeah, you are very right, really. So, in order to have this as a manifold, we will need, free and properness. Otherwise, we may not have a manifold. And then we are into the kind of the word of differentiable stacks, or maybe, the word of stacks. So it's a, generalization of manifolds. Okay, great. So if there are no more questions, let's move to group cohomology. So I want to explain to you in this part, the groupoid cohomology. So let's first of all review the group cohomology. So as we have done throughout the talk so far, we have worked with smooth manifold. So I will again assume the group is a Lie group, but the definition actually works for any group. So we consider the functions. So now since I'm working with Lie group, I can consider smooth functions. We can also just work with continuous functions, or maybe even weaker assumption like measurable functions. There are different versions of group cohomology. So for group cohomology here, we are considering actually tuples of group elements. For the degree K chain space, we are considering functions on this K product of the group. And on this space of functions, this is a vector space, we will consider the following differential. So this is same as what the group cohomology will learn, in the homological algebra. So we can work with, instead of smooth functions, even, rings, like integer rings, or maybe other your favorite ring, that's okay. So for this version of group cohomology, we're using this differential. So this is kind of natural differential from the simplicial structure on this space of product of G's. So which will appear in a moment in the generalization to groupoid. So the differentiable group cohomology, so differentiable here refer to the C infinity functions, and then it's the cohomology of this complex. Okay. So now to generalize our study to groupoids, we need to first of all generalize this space of the simplicial version of the BG. So we are generalizing to the following so-called nerve of G. So this is a simplicial space or simplicial manifold in our setup of Lie groupoids. So you can see here the Gn is usually called the nth nerve space. So let me draw it using pictures. Basically, that means we have in total n arrows in our groupoid. They are all composable, and this is our Gn. And the G0 and the G1, now you can see that we had the G0 and G1 for the set of objects and set of morphisms. Now, to be compatible with the convention, sometimes we will have up 0 and up 1. But that's the kind of the first two. And then we can have the following simplicial structure. I'm only writing out partially the structures because, for the space to write down everything, it takes more time. But basically, you can see this is a generalization of what we just saw for group cohomology. For the first one, we throw away the rightmost. For the last one, we throw away the leftmost. In the intermediate ones, we do the composition. This is the kind of a simplicial structure we can get. Okay, so this is the degeneration map. We can also have the face map. Okay, this is the face map. The degeneration map is to insert the units properly at the right position. So let me not get into that. So with all this together, they form a simplicial sets. And actually, it is a simplicial manifold. So here I wrote down the degeneracy map. It's, as I said, it's the insertion of the unit at the proper position. So with the S, with the D together, we have a simplicial sets. So now we can play it as what we learn in homological algebra. We have a simplicial set. We can consider the space of. So here I just introduce this as a notation for the first one. Now we can consider the generalization of group cohomology to this version. So we consider smooth functions on the nerve space and the face map pullback along the face map provide us the differential. So you can see we have this one is what we're going to use to define the group cohomology. But this one will give us the co-simplicial structure. So we have actually a simplicial complex, a simplicial vector space. We can use it to define a differential like the standard construction. And then with that, we can have the groupoid cohomology. So for this version, as I've repeated several times, this is the smooth version. So this is the smooth groupoid cohomology. Smooth groupoid cohomology.
Sorry, so you cannot do homology because your groupoid is not detailed. So the maps in the other direction will go.
Yep. So if the groupoid is not at all, we have to be careful with the homology. You can try to do it with a choice of the hard system. Then it's more delicate. for étale, it's kind of easier, as Willie mentioned.
But so what I was wondering is whether this complex could be interpreted as computing an X, like applying a home to some resolution. But the resolution, I mean, would need the maps going in the other direction to be defined. And yeah, that's why I asked about the étaleness.
Yeah, so that's a very good question. And I'm not aware of this interpretation for the general groupoids.
Yeah.
But so that's for the group cohomology, and then examples, right? So the examples is for the proper ones. Actually, the cohomology is, not that interesting. It's basically the algebra of smooth functions on the unit space. And it's like the generalization of the cohomology of compact groups. For the continuous cohomology of compact groups, there is no non-trivial high degree cohomology classes. Everything is just the, invariants. So the other is the pair groupoid. So remember, we had the pair groupoid is Morita equivalent to a point. So now if we consider the chain complex we just considered, we actually have smooth functions on the product of manifold. So this one's shows up naturally when we compute Hawkshot cohomology. That's, we have, so this one, actually, it is also, you can check on the topology side, it's the differential we have, it's actually the same as Alexander-Spanier differential, but now we are considering this complex. We're not localizing our complex to the diagonal. So the complex for this cohomology actually is trivial. So it's actually acyclic, except for degree 0. So now, back to our discussion of Morita equivalence, this groupoid is equivalent to a point. This is also compatible because for a point, for cohomology, is only non-trivial at degree 0, no higher ones. So that's this example, and you can say that in some sense, what discussing today is a generalization of this groupoid, of this version. Okay, so now another type of groupoid cohomology, this goes to the kind of the cohomology of classified space. So when we have, so just now we just consider smooth functions, but now we want to include also differential forms, because here we have manifold structure. We can talk about differential forms. So we can look at differential forms on the nerve space. So of course, now we still can pull back along our, phase maps. The pullback map is still well defined, but now we have an extra differential. We have a bicomplex because along the differential form side, we can do the Durand. So we have a bicomplex. So this complex was studied by Bolt and Schumann in the 70s. They were more interested in looking at, the foliation cohomology. So so now we can look at, the Durand differential and this bicomplex. This bicomplex is called the Bolt-Schumann complex. And the Bolt-Schumann cohomology is the total cohomology of this double complex. And yeah, for example, if we consider the Lie group, then the Bolt-Schumann cohomology is the cohomology of the BG, is the cohomology of the classified space. So if we consider, a group action on the manifold, for example, this, in our study of non-commutative geometry, we often consider discrete groups or étale groupoid. Then we can talk about the same version differential forms on the nerve space, this provides a nice geometrical model to compute the cohomology of BG, of the classified space of the groupoid. Okay, great. So that's about the Bode-Schumann complex. So now I need to explain the theorem, I need to discuss this pullback of sheaves along the morphisms. Actually, here we are having something called co-morphisms. So what are we having here? So this is about sheaves of modules over the manifold. As I said, we'll consider C-infinity function modules for our study. And then we have two sheaves. You can let me try to write it. So we have one sheaf, let's see, W over N, and then we have a map F. This goes from M to N, and then we have a sheaf E. So now we will look at the pullback of the sheaf W. This is now a sheaf over M, so we are seeing that we have a comorphism. If we can have a map, we can have a lift of the map from epsilon, the E, to the pullback of W. So the existence of this F is what we call comorphism. So now with this, we can define a more general type of sheaves we can work with over groupoids. So we started with, a general Lie groupoid, and we have a collection of sheaves of modules over each level of our nerve space. That's our EN space. So now what do we require is we require that the phase map and the degeneration map, they have a lift to the level of sheaves. That's the requirement that we are asking. So we want to lift our, structures on the nerve space to the sheaves we have. And with that, so we call it a co-simplicial module of sheaves over the groupoid. So this is the general kind of framework we're going to work with. It will include both the cohomology we just introduced. So Willie, how much time do I have?
10 minutes, 9?
10 minutes?
Yeah.
Okay, great. Yeah, thank you. So now, as I said, I need to work with, a generalization of what we just talked about. We want to have some nice collection of this sheaves. So it's what we call a good co-simplicial module. So it's good basically means we have the following collection of data. So what are we seeing here? So for Lie groupoid, we have the following. So let me write. We have G1, we have G0. So with the surjective submersion properties of source and target, given us every point in G0, we can find the open set, and we can find a local bisection. That's a view tutor.
So it's not a tile, or is it?
Not necessarily at all. For any Lie groupoid, the existence of such a local bisection exists. Of course, for et al, it always exists with the local diffeomorphism. Right. Yeah. So now with that, what do we want is we want this bisection also lives to the sheaves. That's what this kind of information we have. So now once we have this, so this is the kind of bisection property you can see. We want this to be a bisection. Now with this, I can, okay, so what are examples? The examples is when we consider the differential forms, and we have all the maps as we need it. This is actually a good co-simplicial module over the space of nerves of a Lie groupoid. Okay, so now our theorem is the following. So if we have a weak equivalence of Lie groupoids, and if when we have a good co-simplicial complex of co-simplicial modules, complex of modules over the nerve space, we can have the following isomorphism of groupoid cohomology.
When you said on pull back co-simplicial complex on H or on G.
Oh, sorry. This is, you caught me. This is a typo. This should be on H. Let me see. Good. Let me see. Yeah, this is right. This is not right. Yeah. Okay, so let me, go to look at some examples. So first one is when we consider the sheaves to be just the C infinity functions. And then we have the smooth groupoid cochains. And in this version, we recover a theorem of Kreinig and Berendt in the kind of beginning of 2000. So the cohomologies of the two groupoids, if they are Morita equivalent, the smooth cohomologies are isomorphic. But here we don't need to pull back because the pullback of functions is still functions. So we're using that as a property of our statement. So that's for the special case of C infinity functions. Now the other one is for the Bode-Schumann complex. For the Bode-Schumann complex, and we can consider the Bode-Schumann cohomology. So again, if the two groupoids are Morita equivalent, the cohomologies are isomorphic. So you can say, well, the Bode-Schumann complex is computing the cohomology of BG. So when the two groupoids are Morita equivalent, there is a weak equivalence between the corresponding BG and BH. So from the cohomology point of view, the two cohomologies have to be isomorphic. So now we are having it from the smooth category to show they are actually isomorphic. So this is the Bode-Schumann complex. Okay. So my time is almost up. Let me just give you a idea, kind of a crucial idea in our proof. So this is the shift complex. So what we are having, so this idea actually goes back to, I think, Illuzi or maybe even Grothendieck in their study of, the sheaf theory and simplicial sets. So we have the simplicial set. So we have, phase and the degeneracy maps. So now, given us this collection of data, we can shift our simplicial sets in two directions. We can do the left shift. You can see the left shift refer to that we are considering, we shift the complex to the left, K step. I will show you the picture in a moment. Then you'll probably be able to see what's going on more easily from the picture. And once we do the shift, of course, we have to throw away some simplicial structures. We only look at a subset of the data. This one still form, originally we have a simplicial set, satisfy all the identities we want. So now we throw away a part of them. The left is still satisfy the properties we have. So this is actually a new simplicial set. And this is what we call the left shift. We can similarly do the right shift. So now, so you can see the shift are same, but as a set, but the structures actually are different. You will see from here. So this is the right shift of 2 steps. So the whole thing here was the kind of a space of, the face maps we have, right? We have all the structures. Now for the shift, we're taking this corner. Of course, we can also do the other one. And this is kind of the trick we have in order to prove the equivalence. So we build a new groupoid, a new bigger bi-complex. So starting from the weak equivalence. Let me go back to the main theorem we have. Right. Starting from this weak equivalence, we can build a kind of a double groupoids and a double simplicial sets. And then we can map one G from the vertical direction, the other from the horizontal direction. And then the shift kind of a property tells us the inclusion maps are both equivalents of simplicial sets. They have the same cohomology. So with that, we're able to show the isomorphism of the 2 cohomologies. Okay, that's all I want to share with you today. So thank you for your attention.
So thank you very much for a very nice talk, Xian. Are there questions from the audience? Apart from
Yeah, I have a question. So
Yeah, please.
I just wanted to get back to this X picture. So why can we not write this as an X of some convolution algebra? This version of groupoid cohomology?
So it is, so we're not considering, so in the étale case, yes, you can do that. This is, the work of Krennic and Moldijk. Yeah, for the general, it's because of the smooth structures along the fiber direction, say the S fiber or T fibers. I'm not sure you can easily interpret it as the convolution algebra extra functor.
I mean, I suppose that one could like associate to a groupoid some category of, say, left spaces over it. And,
Yes.
yeah, and study equivalence of the spaces over G and the spaces over H, and
Yes.
given by correspondences, and define some X. But yeah, but the point, I mean, is that these cohomology theories are already there, and it is not at all obvious that they can be interpreted in this way, so one has to by hand show that equivalence deserves.
Right.
If one knew that such a thing, so Devarshi is sharing an article.
Yeah, I mean, I was recently talking to these guys who had asked a similar question, and like, they worked out a Morita theory for Lie groupoids, and they used a version of this smooth convolution algebra. So
Yes. Yeah. So I have noticed this work. Yeah. So
right.
this is, I think, the beginning of maybe the more developments. Yeah.
Right.
Yeah. Yeah.
Okay, so we have to see the paper.
Yeah, I guess, it's certainly a very interesting direction to develop more. Yeah, but I guess as Willie pointed out, so far the machineries haven't been developed to cover everything in a kind of a coherent way, in a kind of unified way. Yeah, so and in another project with Marcus Flom and Hazel Postuma, we had a project of computing the Hochschild homology of the convolution algebra for Lie groupoid. Yeah, so but the cohomology turns out to be more complicated. It's more, we need to have some Brzezinski models for the groupoid. So it's not as simple as what we are having here for this example or the Bott-Schumann complex. Some generalization of it will appear, but it's more involved.
Right.
Yeah.
But when you say you try to compute the Hochschild homology of some convolution algebra, what is the tensor product you use? Is
Well,
it
we
some
use
like completed tensor product?
Very good question. Yeah, in that version, we have to work with, some kind of Fréchet or maybe more precisely this phonological algebra and the phonological tensor product.
Right.
Yeah, the theory developed by Ralph Meyer.
Right.
Okay. So are there any further questions or comments? Otherwise, I will stop the recording here.